Hi, everyone. Welcome to the 2024 P4 workshop. I am really excited to see so many of you here. Just like all the previous years, there are a lot of familiar faces, but there are also quite a few new faces. So I feel energized by the participation from the P4 community. P4 completed about a decade of its journey. So I thought I would, particularly for the benefit of those who are coming new, I would spend a little bit of time, uh, trying to remember the journey of the last decade. So the paper, the seminal paper, which actually originated the name of P4, which is Programming Protocol Independent Packet Processor. If my memory serves me correctly, this was published in 2014. And recently, it was voted as one of the most widely referred papers in the networking technology area. And then in 2015, the first P4 language spec, which at the time was known as P414, that was published. Couple of years later, the control plane part of the P4 specification, the P4 runtime, was released. And at around the same time, very much evolved a very different looking language syntax that came up, that is P416. We are still using it. In 2018, P4 joined Open Networking Foundation, or ONF. And around 2019, Barefoot, which was the primary driver of at least the silicon-oriented P4 technology at the time, that was acquired by Intel. Then we come to something that is not so positive. It was a sentimental blow for many of us, but in 2023, Intel stopped development of future generations of Tofino. But within other Intel products, including Intel IPU, we still keep doing a lot of work on P4. And specifically for Tofino, something that will go through a formal announcement, but I wanted to say that by end of this month, we are going to open source pretty much all the bits of Tofino software, compiler, tools, the pipe manager, and other kind of constructs. So that's good. 2024. 2024, P4 also moved from ONF to Linux Foundation. So we also have a little bit more visibility and also the support from the Linux Foundation community. After this, I thought, going through the journey of P4, I would similarly go about my own journey or my team's journey on P4. Before I start my slides, one disclaimer. This is not supposed to be a beating the drum or advertisement of whatever we did with P4. This is more like my poor attempt to show in how many different ways P4 can be creatively used in a lot of technology areas. So I'll go through some of that. So right after joining Intel, one project that we did was an FPGA-based OVS offload card. That's called Cascade Glacier. The specifications of hardware specifications of the card that you see here is not important, but what we were able to do with P4 is the packet processing pipeline of Cascade Glacier could be generated from P4. You could start with a P4, and then there was a tool that would generate the Verilogs for that can then be programmed within the FPGA. And we mentioned Mihai's name a couple of times. Mihai gave me enormous amount of flack for not writing a proper compiler backend, but it was just me working on it. So, this is the shortcut that I decided to take. But that was our first P4 project within Intel. Um, this is actually an older version of my slides. It seems like the newer version. Anyway, it doesn't matter. So another project that we did shortly after is something that we call P4 DPDK. And in the P4 DPDK project, what we did is for every P4, there would be two different output formats that were available. One is called a spec file, which is almost like a text description, and another option is to generate a binary. But in both formats, it used to generate some VLIW code that the P4DPDK library itself could then interpret and do packet processing, DPDK-based packet processing based on the P4 rules that are specified. And let me now go back. My slides are a little bit disorganized because so one of the reasons that we did this project was for this initiative that we started around early 2020, which is Infrastructure Programmers Development Kit, or IPDK. And IPDK had P4 as a central pillar of everything that we did for IPDK. And our goal was to start from what we call infrastructure as a service, which is mainly vSwitch, storage, and crypto, to come up with abstraction APIs for these things, how to do it on IPUs, DPUs, and other kind of targets, such as you see the targets listed here. There's an IPU or DPU target. There's also a switch target. IPDK ran efficiently on Tofino as well. And if someone wanted to start prototyping on IPDK, they could have started on a CPU target, prototype all of these things on a CPU, and then move to hardware without rewriting any of the APIs. The APIs stayed consistent. So for that CPU target, we built that P4 DPDK library that I mentioned before. It could provide a reasonable throughput running on processor cores. So that was what P4 DPDK and IPDK was about. All of these things that I mentioned here, network, storage, crypto, these were all P4 based. And I'll talk more about some of these things. One of the areas that we tackled as part of both IPDK as well as our general software offering for the IPUs is how to efficiently offload Open Virtual Switch, or OVS. Those of you who are familiar with OVS, you know that there is a software optimization that the community did, which is a great optimization. It involves two levels of caches. One is a microflow cache, which is kind of like a flat flow cache. Every new flow will occupy an entry in the microflow cache table. And then there was more like a wildcard match type of capability built in something called megaflow cache. And the hardware offload approaches that were taken, not just by certain groups within Intel, but some of our competitors also, is to look at what is coming out of the megaflow cache and then try to offload it on hardware as best that they could do. There's one problem with this approach. The problem is what I try to articulate here, that when it is coming from the SDN controller, the so-called intent of the application is pretty well known. There could be, an ACL application or a L3 lookup application, etc. Right? And then anticipating these needs, the hardware vendors have provided certain kind of hardware support. For instance, TCAM match, or longest prefix match, or exact match, etc. So at the top level, at the SDN control level, these application intents are very well understood. Once you go through these two levels of cache, not so much. I mean, one flow is pretty much indistinguishable from the other flow, so then it becomes a lot of guesswork, a lot of busy code to be able to map it efficiently to the hardware. So with the P4 approach, we are like, let's just do away with the caches. We could go directly from the application level tables to the hardware tables. And this provided very good performance, in particular, a very good flow setup time. Because OVS is fundamentally reactive. Once you recognize a new flow, the first packet of that new flow goes to the user space, its match action policies get configured, and then it gets sent back. And from that point onwards, all of the packets of that particular flow will go through that, whether it's a hardware data path or kernel data path, whatever it is. So this is the innovation that we brought to move from to do away with the reactive programming and go directly from the SDN controller directly to the hardware tables. And the reason that we did that is, if we talk about Intel as hardware vendor, we needed to support many different platforms, switches, NICs, FPGAs, softwares, and there was also this other thing that as we delved more into this thing became apparent that there are also a lot of custom V switches that are not upstreamed. Alibaba has its own called Alibaba V switch or AVS. Tencent has its own. There are a lot of these, and how many purpose built hardware optimization are you going to do? So this one, gave that flexibility of being somewhat agnostic to the internal implementation. And that's how we came up with this P4-driven vSwitch. And this is the architecture. There was as you can see, as we discussed this idea in P4 retreat, there was a question on whether there is a need to throw away a lot of these APIs that are already part of OVS. No, it is not. If you see the architecture, all the blue ones are actually from OVS. We just introduced some specific blocks that provides a different path for programmability, retaining most of the compatibility with OVS. Another thing that we did was P4 programmable IPsec. So here within the IPU, there is a inline crypto processor that can process encrypted packets at line rate. And so every packet is going to go through that particular processor, and a decision will be made on whether that packet needs encryption or decryption, or it will be just passed through to the rest of the pipeline. So we moved some of these decision making to the P4 file. Another way that a P4 programmable IPsec helped is some of our customers wanted to do custom VXLAN encap decap, and they really didn't want to disclose upfront some of those details. By moving that to P4, we could provide a path where they could update their own P4 and not having to disclose that to us. So that was our P4 IPsec. So this is an example of how one can do custom tunnels using P4 programmable IPsec. And after that, we are always talking about moving from the different layers of these services, starting from infrastructure as a service. Then we started looking into platform as a service, mainly containers, service meshes, and those kind of things. So we also did a project on Kubernetes offload on IPUs using P4. So the Kubernetes offload approaches, I mean, there is kernel-based approaches. There is a eBPF backend done by Cilium that is deployed in certain data centers. And then there is also a DPDK, which uses a specific flavor, the Calico flavor of Kubernetes. This project started with that Calico flavor of Kubernetes, and this is how we were able to use P4 to map certain things to specific rules and flow tables. So that was also a pretty interesting project. Another project that in very short time we're going to spend a lot of time on is our attempt to integrate these two very, very important pieces of networking technology, the Linux networking stack with the P4 programmability. And for that, we uh, did a project called P4TC. Where is the name TC coming from? You know that the Linux TC is one of the popular interfaces for network programming. And what the compiler backend that we did, what it is going to do is it is going to generate the TC scripts, and then those TC scripts can be used to uh, program the rules within the kernel. So that's one of the backend that we developed, which starts with a P4 and generates the TC scripts. That's the software version of it. And you can have an identical digital twin version of it where it actually gets accelerated on hardware. And for that, of course, you're going to use the hardware specific compiler. So that's kind of our journey. I'm sorry, since this is not the latest version, some of these are. But so as you see, almost every year we were able to find new creative ways of using P4. And I sincerely hope that this is not going to stop. I am currently also leading the software effort of AI networking chip, and we will surely find some way of using P4 there. It remains to be fully developed. But I wanted to take a minute or two and think about um, some of my experience, some of my observation about people. Again, just my personal belief that I think that the technology ramp or the difficulty of technology ramp up on P4, in my personal opinion, it's been a bit of a myth. I have 5 sites distributed internationally in multiple continents, and they were all able to ramp up on P4 without a lot of difficulty. So I don't think that was that big of a challenge. In fact, quite often it was probably more of a imperfect mapping of a particular hardware target to what the P4 actually tries to do. That became more of a challenge. I think P4 leaves a lot of details a bit vague and ambiguous, and lets the compiler deal with those ambiguities. Some people might say, why isn't P4 more specific? My personal view is that that level of ambiguity is actually not bad. It gives flexibility for the different hardware vendors, accommodates different type of pipeline capabilities. I think that currently we are at a technology crossroad where all of these excitements about AI, ML, large language models, and the need for just pure high speeds and feeds, not a lot of programmability that may come as a challenge to the whole data plane programming community as a whole, and also to P4. And I think that some future P4 integration within AI/ML ecosystem is definitely possible. And I think in this workshop today, we are going to hear some more of that. Another topic that is often coming up is, how it is not easy to map certain hardware capabilities to P4, and therefore some sort of a instruction set definition or virtual machine definition for P4 can simplify, enabling that hardware support. And again, today itself, we are going to hear more about it. I'm not going to beat about the bush. I think Tofino cancellation was an emotional impact for the community, and I think the upcoming open sourcing of Tofino software is going to be beneficial. I think it is going to foster innovation in many different areas. I would like to, conclude by saying that the strength and passion of the P4 community is our biggest strength. There is a lot of you who have invested a lot in the technology and continue to invest, and that will definitely take us forward. My personal belief is P4 is here to stay for many decades to come. And if you want to join hands and collaborate, please reach me at deb.chatterjee@intel.com.
We have two microphones set up in the back of the room here on this side, so folks over here have to walk a little bit further, but if there's questions, anybody have any questions right now for Deb? He's actually coming right back up in a minute, so I think you have a question. Good.
Yeah, so as somebody who's sort of building an accelerator for both P4 and eBPF, and you also mentioned the importance of sort of an intermediate format for P4, which I think is really important as well. If you look at how LLVM is enabled like Clang in the regular programming language world, what are your thoughts on the sort of interaction and sort of future of eBPF and P4, and how do they relate to each other, especially in the context of like SmartNICs and accelerators?
From a pure software point of view, my personal view is that, there are many cases where it comes across that, either P4 or eBPF can do the same thing. From a hardware point of view, it is actually a very different story. I mean, with the eBPF's constrained definition of a virtual machine with a specific instruction set and a specific number of registers, that's a lot harder to map capable hardware to that one. And I think as far as providing support for new and innovative kind of hardware, P4 definitely has an advantage. I'm not trying to undermine the huge eBPF programming community. I mean, of course, they have done a lot of cool stuff and will continue to do that. But I think where P4 definitely has an advantage, as I hope some of my slides showed, is kind of expanding, doing a little bit of out of the box, and being able to use the capabilities of the hardware.